I am Raghavan, Chemistry Faculty from ALPHORES College. I invite you all for the ALPHORES Chemistry e-learning classes, session 40th. Okay, in the last session we started the chemical properties of alkali metals. Alkali metals, that is 1A group elements. Alkali metals means 1A group elements. They are lithium, sodium, potassium, rubidium, cesium and francium. Okay, so we completed oxides, we completed hydrides, we completed, and now we already started the halides. Okay, alkali metal halides. So the halides, lithium 2, cesium, they form the corresponding halides, fluorides, chlorides, bromides, iodides, like that. Okay, that is sodium fluoride, sodium chloride, sodium bromide, sodium iodide. So all halides are formed. That is lithium fluoride. Among all the halides of lithium fluoride is little more ionic, and as the size of the anion increases, the ionic nature decreases, as we said that. So lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Okay, so in all these cases the cation is common, lithium ion is cation is common, and the nature of the substance is decided by anions according to the Fajan's rules. Okay, smaller the size of anion, smaller the anion favors more ionic. That means lithium fluoride is more ionic compared to other halides of lithium. Okay, and lithium iodide is predominantly least ionic, means more covalent in nature. Okay, so that is about halides of lithium. Suppose if you consider the chlorides, so lithium chloride, sodium chloride, potassium chloride, rubidium chloride, that means down the group, cesium chloride, these are all chlorides of alkali metals. So now the chlorides of alkali metals, which is more ionic and which is less ionic? Okay, the important point, that is, so according to the Fajan's rule, larger the size of cation favors more ionic. Larger the size of cation, so it is Cs plus, rubidium plus, potassium plus, sodium plus and lithium plus. Larger the size of cation favors more ionic. Therefore, cesium chloride is more ionic in nature. Okay, from top to bottom, as the size of the cation increases, ionic nature of the substance increases. So from top to bottom, ionic nature increases. Okay, ionic nature increases from top to bottom. When ionic nature increases, ionic compounds are freely soluble in polar solvents like water. That means solubility of these halides also increases from top to bottom. Solubility of the halides increases from top to bottom. Now coming to the important point, conductivity of the substances. Conductivity. Okay, we are not discussing all the properties of ionic compounds. Okay, we are discussing the properties of these halides in the group. So one is conductivity of these halides. Conductivity. So conductivity directly proportional to general concept. Conductivity directly proportional to mobility of ion. Mobility of ion. Mobility of ion, and it is inversely proportional to the size. Smaller the size, more mobile, that is more conductive. That is a straight away concept, standard concept that cannot be changed. Okay, now when it is dissolved in aqueous solution, the conductivity, now that is in aqueous solution, what is the conductivity of the substances? In aqueous solution, let us see, in aqueous solution, that is lithium gets more hydrated. Okay, lithium gets more hydrated. So therefore what happens? So when lithium gets more hydrated, the radius of lithium ion is much more bigger in size. Okay, because hydration energy is inversely proportional to the size. So lithium cation gets more hydrated, therefore the radius ion becomes bigger in size. So hence the lithium chloride is less conductive in aqueous solution due to the less mobility of lithium cation. Due to less mobility of lithium cation, lithium chloride is less conductive. From top to bottom, radius of hydrated cation, remember, radius of hydrated cation decreases. So therefore, due to small size of hydrated cation, cesium cation, so cesium cations small size, therefore the mobility of cesium ions is very easy. So therefore, since it is more mobile, so therefore that is more conductive. That means in aqueous solution conductivity increases from top to bottom in the group. Okay, so that is the conductivity of the halides in the aqueous solution increases from top to bottom. Don't expect that cesium ion is bigger in size, that is why cesium conductivity is less. So that is in the aqueous solution conductivity, because in solid state there is no free ions. In solid state, all these ions are tightly packed in the three-dimensional lattice. Okay, that is why in solid states ionic compounds are very bad conductors of heat and electricity due to the not availability of the free mobile ions. So the conductivity always we have to check in aqueous solution. In aqueous solution, what happens? So the hydrated lithium cation is much more bigger in size. That is why lithium ions does not mobile. So since the mobility of lithium ions is very less, so therefore the conductivity of the lithium is also very low. Okay, from top to bottom, the size of the hydrated cation decreases, therefore the mobility of ion increases. As a result, the conductivity increases of halides. Okay, this is about halides completed. Now next, coming to the that is carbonates and bicarbonates. Okay, let us take the next concept of carbonates. Alkali metal carbonates. See, that is how the carbonates are formed. For example, lithium oxide, when reacts with carbon dioxide, it forms the corresponding lithium carbonate, Li2CO3. That means generally we can say that alkali metals can form M2CO3 type of M2CO3 formula of carbonates. M2CO3 formula of carbonates. Lithium carbonate, like this. Lithium carbonate. Next one, sodium carbonate, Na2CO3. Potassium carbonate, K2CO3. Okay, that is rubidium carbonate, Rb2CO3. Then cesium carbonate, CS2CO3. So these are all carbonates of alkali metals. Okay, carbonates of alkali metals. So alkali metals can form M2CO3 formula type of carbonates. So these are all the formulas of carbonates. So now the stability of the carbonates, the thermal stability of the carbonate, except lithium carbonate on heating, it decomposes into lithium oxide and carbon dioxide. It liberates carbon dioxide on heating. So except lithium carbonate, the rest of the carbonates of alkali metals are thermally stable. They are all thermally stable. All these carbonates are thermally stable. That means on heating they do not undergo decomposition. So remember, this point is very important. Okay, except lithium carbonate, the rest of the carbonates of alkali metals are thermally stable. And what is the nature of these carbonates? Okay, first point, lithium carbonate is thermally unstable. It decomposes on heating, gives lithium oxide and carbon dioxide. That is important point. Then the rest of the carbonates of alkali metals are thermally stable and they are all solids. Okay, so all these carbonates are solids only. So it is thermally unstable. The rest of the carbonates are thermally stable. And the next one, so what is the solubility of these carbonates? So carbonates, when dissolved in water, they soluble in water and they forms the corresponding aqueous solutions, that is alkali nature of the aqueous solution. For example, sodium carbonate when dissolved in water, it forms sodium hydroxide, NaOH plus CO2 gas is liberated. That's all. It is balanced. When sodium carbonate, when metal carbonate is dissolved in water, forms the corresponding metal hydroxide and liberates carbon dioxide gas. Okay, this is that is when carbonate is added to water, the carbonate compound dissolves in water and forms the corresponding hydroxide. That means it gives the corresponding alkali solution. That means lithium carbonate gives lithium hydroxide, sodium carbonate can give sodium hydroxide, potassium carbonate can give potassium hydroxide, rubidium carbonate can give rubidium hydroxide, cesium carbonate can give cesium hydroxide. Yes, that means what is the nature of these carbonates in the aqueous solution? Yes, in aqueous solution all these carbonates can produce alkali solutions. Therefore, their nature is basic in nature. Metals, metal oxides, metal hydroxides, metal carbonates and metal bicarbonates all are basic in nature. That is why they are called alkali metals. Okay, so sodium carbonate, example I took sodium carbonate. Okay, so they are all soluble in water and they produce the corresponding metal hydroxides and liberates carbon dioxide gas. Okay, that is the point. Now, solubility of these carbonates from top to bottom, solubility of the carbonates increases. When you say that cesium carbonate is strong basic, that means when it is strong basic means what? Strong in the sense what? It possesses high degree of ionization. So from top to bottom, the degree of ionization of the carbonate increases. That means the basic strength increases. Okay, that means the solubility of the carbonates increases from top to bottom. First point, solubility of the carbonates: lithium carbonate less than, sodium carbonate less than, potassium carbonate less than, rubidium carbonate less than, cesium carbonate. Okay, the solubility of the carbonates increases from top to bottom. That is very important point. Next one is that is solubility. How we can represent that solubility? Let us write that solubility order. That is lithium carbonate Li2CO3, Li2CO3 less than Na2CO3. It is less than K2CO3. It is less than Rb2CO3. It is less than cesium carbonate CS2CO3. So that is solubility order, and that is nothing but the order of basic strength. Okay, basic strength also increases from top to bottom. Solubility also increases from top to bottom. All these carbonates are solids and thermally stable except lithium carbonate. Okay, that is important point. Okay, that is about carbonates. Now coming to the bicarbonates. Bicarbonates of alkali metals. Bicarbonates of alkali metals, that is 1A group elements. Yes, alkali metals can form MHCO3 type of bicarbonates. MHCO3 type of bicarbonates. Okay, general formula is MHCO3 type of bicarbonates. They are all solids. Okay, so alkali metals, that is alkali metals are 1A group elements. They form MHCO3 type of solid bicarbonates. Example formulas, that is lithium bicarbonate. Theoretically we can write like this, but lithium bicarbonate does not exist as solid. Okay, lithium bicarbonate, sodium bicarbonate. Okay, sodium bicarbonate. Next one, potassium bicarbonate and rubidium bicarbonate and cesium bicarbonate, CSHCO3. Okay, they are all bicarbonates. Okay, so the alkali metals can form solid bicarbonates. Okay, alkali metals can form solid bicarbonates, and we know that sodium bicarbonate commonly known as baking soda. It is available as solid only. So that means the bicarbonates of alkali metals are solids. Okay, so now what is the nature of the bicarbonates? Bicarbonates are basic in nature because when dissolved in water, it gives the corresponding hydroxide only. That means it gives, that is NaOH plus CO2 gas is liberated. CO2 gas is liberated. So according to that we can balance the equation. So that means sodium bicarbonate when dissolved in water forms the corresponding hydroxide, that is sodium hydroxide, and liberates carbon dioxide gas. Okay, so due to the formation of sodium hydroxide we can say that so that is sodium bicarbonate is basic alkali in nature. From top to bottom basic nature of the bicarbonates increases. That means lithium bicarbonate is less basic than sodium bicarbonate, sodium bicarbonate is less basic than potassium bicarbonate. So from top to bottom the basic strength of the bicarbonates increases. Now coming to the solubility of the bicarbonates. Yes, similarly as the trend observed in the carbonates, the bicarbonates are also soluble in water. The solubility of the bicarbonates increases from top to bottom. Lithium carbonate, lithium compounds are less soluble. Lithium compounds are less soluble. It may be halides, or it may be oxides, or it may be hydroxides, or it may be carbonates or bicarbonates. Lithium compounds are less soluble in water due to higher lattice energy. That point you should remember. Lithium compounds are relatively less soluble in water due to higher lattice energy. That is a point we should remember. Okay, suppose any compound is less soluble in water means it is possessing higher lattice energy. Okay, so that is the concept. So now let us see another important question like this. When alkali metal, that is sodium, when sodium metal is exposed to air, what happens? When sodium metal is exposed to air, so what happens? It can react with oxygen present in the air. It reacts with oxygen of air and forms. It reacts with oxygen of air and forms sodium oxide. Okay. So what happens when sodium metal is exposed to air for long time? Okay. On long standing, what happens when it is kept in the air? Sodium reacts with oxygen of air and forms sodium oxide. This sodium oxide, this substance absorbs moisture from the air. It absorbs moisture from air. That means it reacts with water molecules present in the moisture and forms sodium hydroxide, NaOH. NaOH. Okay. This NaOH absorbs carbon dioxide from air. This NaOH absorbs carbon dioxide from air. Let us see. NaOH absorbs carbon dioxide from air. It is converted into sodium carbonate. Sodium carbonate plus H2O. Okay, it forms sodium carbonate, Na2CO3. That is the reaction. So what happens when sodium metal exposed to air for long time? First it is converted to oxide, then it is converted to hydroxide, then by absorbing carbon dioxide gas it is converted finally into sodium carbonate. That is one important reaction. They will ask you in the objective type questions. So that is sodium metal reacts with oxygen present in the air, forms the compound X. Okay, instead of this they will give X. So this X compound with water molecules forms the compound Y. The compound Y is nothing but our sodium hydroxide. This compound Y absorbing carbon dioxide forms compound Z. So what are X, Y, Z in the reaction? They may ask you like this. Or what is Z in the reaction? So that also you can expect. Okay, like this objective question is important. Okay, that is carbonates and bicarbonates we completed. Okay, then what are the nitrates? That is, let us see nitrates of alkali metals. That is lithium nitrate. Solubility of nitrates, NO3. Lithium nitrate. From top to bottom, the solubility of nitrates also increases. See, that is lithium nitrate less than sodium nitrate, less than potassium nitrate, less than lithium nitrate, less than sodium nitrate, NaNO3, less than potassium nitrate, KNO3, it is less than rubidium nitrate, RbNO3, it is less than cesium nitrate. Cesium nitrate. That means the solubility of the nitrates, solubility of hydroxides, solubility of nitrates, solubility of carbonates, solubility of bicarbonates we should remember, because all these points are important for objective exams. Okay. So far we completed from the chemical properties of alkali metals. We have done hydrides, that is first one. Oxides we have completed. Oxides. Then oxides, in this we have, that is M2O type of monoxides and M2O2 type of peroxides and MO2 type of superoxides completed. Okay, we completed all these different types of oxides. Next, we also completed hydrides. Hydrides. Alkali metals can form MH type of ionic hydrides. MH type of ionic hydrides, that is LiH, NaH, KH, RBH and CCM hydride. Okay, MH type of hydrides. And we have done, that is halides. Halides. What are the halides we have completed? So that is alkali metals can form MX type of ionic halides. MX type of ionic halides, that is lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, cesium fluoride. So they are all fluorides from top to bottom in the group. So that means they form the corresponding halides. Next one, chemical properties of these halides. Next one, carbonates. Carbonates. So what are the carbonates they form? So they form, alkali metals form M2CO3 type of carbonates. M2CO3 type of carbonates and bicarbonates. Bicarbonates. Alkali metals can form MHCO3 type of bicarbonates. MHCO3 type of bicarbonates. Okay. And we can also explain like, see, sulfates also we can take, nitrates also we can consider. But the important one, oxides important for us, and halides are very important. Carbonates are important. Okay, bicarbonates. Okay, right. Another important point is, see how we can determine sodium bicarbonate and sodium carbonate. Sodium bicarbonate and sodium carbonate. So they can be easily identified by the indicator, that is sodium bicarbonate, aqueous solution of sodium bicarbonate. So when phenolphthalein indicator is added to aqueous solution of sodium carbonate, so that is phenolphthalein can produce intense pink color with strong basic medium. So therefore the aqueous solution of sodium carbonate with phenolphthalein indicator, this gives pink color. That is why if the solution gives pink color, we can say that it is it's a carbonate solution. That is why, being it is strong basic, it can produce dark pink color with phenolphthalein indicator. So now when the same phenolphthalein indicator is added to the aqueous solution of bicarbonate, due to less basic nature, the solution remains colorless. The solution which remains colorless upon adding phenolphthalein indicator, so it is, if it is colorless, then we can identify it is a bicarbonate solution. Okay, so that is how we can identify the carbonate and bicarbonate. Okay, that is called qualitative analysis. That is analysis. Okay, so we can identify that bicarbonates and carbonates. So now carbonates and bicarbonates we finished. Halides we completed. Okay, hydrates are also we completed. Then oxides we completed. Next we have extraction of sodium metal. So what is the extraction of sodium metal? See, extraction of sodium can be done by different methods are there. Extraction of sodium can be done by different methods. Okay, that is, sodium metal can be extracted by, one is Castner process, that is Castner electrolysis method. And the second one is Downs process, Downs electrolysis method. Castner electrolysis method and Downs electrolysis method. So in Castner electrolysis method, the fused sodium hydroxide solution is electrolyzed. Fused sodium hydroxide solution, that is fused caustic soda, is electrolyzed. Fused caustic soda is electrolyzed. So in the process we get sodium, because in first year you don't have that extraction process, but I am telling you that is preparation of alkali metals. Okay, just I am giving the idea about so how we can prepare sodium and how we can prepare sodium by this method. Because why it is only electrolysis method, why we cannot use chemical methods? Because highly reactive metals or highly reactive non-metals can be isolated from their minerals, from their ores. So that is by only electrolysis, because electrolysis method is the sophisticated advanced technical method to isolate the required element from its ore. That is because sodium is highly reactive alkali metal, therefore it can be isolated by electrolysis method. What is the method we said? Castner electrolysis process. What is the Castner process? So very simple to answer like this. Fused caustic soda is electrolyzed. Fused caustic soda is electrolyzed in presence of iron cathode and nickel anodes. Iron cathode and nickel anode. Sodium metal is deposited. Okay, that is Castner process. Next, Downs process. Downs process. So in this, sodium metal can be extracted from brine solution, that is fused NaCl solution, brine solution. Okay, the brine solution is electrolyzed. Brine solution is electrolyzed in presence of iron cathode, that is steel cathode, iron steel cathode and graphite anodes. Okay, I repeat, the brine solution is electrolyzed in presence of steel cathode and graphite anodes. During electrolysis, sodium metal is extracted, is collected at steel cathode. Okay, that is Downs process and Castner process. Okay, so these are the introduction to the extraction of the sodium metal. Okay. Anomalous properties of, what are the anomalous properties of lithium? Next heading, anomalous properties of lithium are how do the lithium difference in the properties with other alkali metals? That means anomalous properties of lithium. Anomalous properties of lithium. First, why it has to exhibit anomalous properties? Due to small size. Due to small size. Due to small size, lithium shows different properties. So, what are the different properties? Small size. Small size. Due to small size, it possesses high ionization energy, and it also possesses high polarizing power, or you can say polarizing ability, high polarizing ability. And fourth point we can say high polarizing ability and high lattice energy. Lithium also shows high lattice energy. High lattice energy. Okay. So because of high lattice energy and high polarizing power, we can say that lithium predominantly can form covalent compounds. Okay. So what are the special properties of lithium? Lithium shows small size. Due to small size, okay, due to small size, it shows high ionization energy. Due to small size, it shows high polarizing ability. Due to small size, it shows high lattice energy. Okay, and it can also shows it can also exhibits high hydration energy also, because due to small size, high hydration energy. And remember, okay, for a particular compound, when it is soluble in the aqueous solution, the solubility, the matters the lattice energy and hydration energy. Remember that. So if lattice energy of the compound is greater than its hydration energy, lattice energy of the compound is greater than its hydration energy, then the compound is less soluble. The compound is less soluble. Or if lattice energy is less than its hydration energy, that means hydration energy is greater than lattice energy, then we can say that the compound is more soluble. Okay, so this point you must remember, that whenever the compound is soluble in water, that means when it possessing lattice energy and both hydration energy, when it is more soluble in water, means hydration energy of that compound is more than its lattice energy. Okay, so that is lithium exhibits the special properties due to small size, high hydration energy, high polarizing ability, high lattice energy and high hydration energy. And we can also say that lithium, due to small size, lithium can react with atmospheric air. That means when lithium metal is heated in air, it reacts with oxygen directly and forms lithium oxide, Li2O. And lithium can also combine with atmospheric nitrogen, and forms lithium nitride, that is Li3N. Okay, that is a special property of lithium. Lithium can form lithium oxide and lithium nitride when burnt in air. When burnt in air, it reacts with oxygen, forms lithium oxide. When burnt in air, it can also react with nitrogen directly and forms lithium nitride compounds.